Hello and welcome, fellow space explorer. Take a slow breath and allow your body to settle as the day quietly fades away. If you find comfort in calm, factual journeys through the universe, consider subscribing. It helps this space grow, and it ensures these gentle, science-based explorations are always here when you need them. Tonight, you're not here for fiction or imagination. You're here to understand something real. Above you, the night sky appears peaceful and familiar. One constellation stands out clearly, Orion, a shape you may have known for years. But what you see is only an outline, a flat pattern hiding immense depth, distance, and scale. So now, settle in, look upward with quiet curiosity, and begin by observing Orion exactly as it appears from Earth. Calm, familiar, and waiting to be understood. You step outside under a clear night sky and let your eyes settle into the darkness. Above you, a familiar pattern stands out with unusual clarity. 3 bright stars form a short, straight line, evenly spaced, easy to recognize even from a city edge. This is the belt of Orion, an arrangement that has guided human eyes for thousands of years. Without effort, your vision connects the dots, tracing shoulders and legs, creating a figure that feels stable and complete against the moving sky. What you experience first is not distance or size, but brightness and position. Your eyes respond to light that has traveled across space and atmosphere, arriving at your retina as tiny packets of energy. The brain is skilled at organizing these signals into shapes, especially when contrast is strong. Orion stands out because several of its stars are bright and close together in angular terms. Angular size is how large something appears from your point of view, measured not in kilometers, but in degrees across the sky. You hold your arm out and notice that your thumb covers a small patch of stars. That simple gesture hints at how astronomers describe the sky. From horizon to horizon spans about 180 degrees. Orion, from the raised club to the extended foot, occupies a region a little more than 20 degrees tall. It looks large because it spreads across a significant fraction of your visual field, even though each star is unimaginably distant. At this moment, your perception has no access to depth. The stars appear pinned to a single surface, like points on a dark dome. This is not a flaw of vision, but a natural consequence of how light reaches you. Without motion or reference points, the brain cannot easily judge how far away isolated lights are. A nearby candle and a distant lighthouse can appear similar in size if their brightness aligns just right. The night sky operates under the same principle. Brightness becomes your main clue. Some stars glow strongly, others faintly, and your mind instinctively associates brightness with closeness. In everyday life, that assumption usually works. A nearby streetlight looks brighter than one far down the road. In space, however, stars vary enormously in how much energy they produce. A distant, powerful star can outshine a closer, quieter one, misleading your intuition without violating any physical law. As you look at Orion, Betelgeuse draws attention with its warm, reddish light, while Rigel shines sharply blue and white. Both appear prominent, yet their brightness comes from very different physical causes. Your eyes do not register their true sizes or distances, only the final intensity of light after it has spread outward and traveled through space. This flattening effect makes the constellation feel like a picture rather than a volume. The human brain excels at pattern recognition. When stars appear near each other on the sky, your mind links them automatically. These links are cultural, historical, and neurological rather than physical. The stars of Orion are not bound together as a single object. They do not form a rigid structure or occupy the same region of space. Their apparent grouping is a result of perspective, like distant mountains lining up from one viewpoint while being separated by many kilometers. Still, the pattern is reliable. Night after night, year after year, Orion rises and sets in predictable ways. Earth's rotation carries the sky overhead, and Earth's orbit slowly shifts the seasonal backdrop. These motions are steady and measurable, giving the illusion that the stars themselves are fixed. This stability allows your mind to relax into recognition, trusting that the familiar arrangement will remain in place long enough to be learned. You may notice that Orion seems to tilt or change orientation during the night. Early in the evening, the belt may slant one way, and hours later, it leans another. This is not Orion turning, but you turning with Earth. As the planet rotates, your viewpoint shifts, changing how the star pattern aligns with the horizon. The stars themselves maintain their positions relative to one another on human timescales. When you lie back and watch, the sky feels like a vast ceiling. This sensation is deeply rooted in human perception. The dome illusion arises because all stars are effectively at infinite distance compared to everyday objects. Your eyes cannot focus on them individually in terms of depth, so they collapse into a single surface. This illusion has shaped navigation, mythology, and early science, long before precise measurements were possible. Ancient observers described Orion as a figure because the mind seeks meaning in patterns. Modern astronomy keeps the pattern for convenience, not because it represents a physical truth. The names help observers communicate and orient themselves, but the science moves beyond the outline. What matters now are positions, motions, spectra, and distances, all measured with careful instruments rather than intuition. As you remain under the sky, you begin to sense a quiet mismatch between what you see and what you know must be there. The stars feel close enough to belong together, yet you understand that light takes years to reach you. Even without numbers, the idea of distance begins to stretch gently in your mind. The calm realization forms that the sky is deeper than it looks. This understanding does not disrupt the beauty of Orion's shape. Instead, it adds a subtle layer beneath it. The pattern remains useful and comforting, while the knowledge that it hides a three-dimensional arrangement waits patiently beneath the surface. Your eyes rest on points of light, while your thoughts begin to reach outward, curious about how far apart those points truly are. As the night continues, the idea of size becomes less about appearance and more about measurement. The sky invites you to consider angles, distances, and scales that do not match daily experience. Orion remains steady overhead, a familiar guide, while a deeper question settles quietly into your thoughts. How wide is this pattern in space? Once the flat sky opens into depth, the stars do not answer directly, but the tools of science exist to ask carefully. Instruments compare positions over time, noticing tiny shifts against more distant backgrounds. Light itself carries clues about motion and distance, encoded in color and intensity. These methods transform the sky from a picture into a structure. You breathe steadily and let Orion remain in view. The meaning of size separates from appearance, becoming something measured, defined, and quietly expansive. This calm distinction prepares your thoughts for distances that exceed intuition without urgency and invite observation to replace assumptions. You raise your gaze again to the sky and notice how naturally your eyes measure space without numbers. Distances feel intuitive on Earth. A tree across a field looks farther away than one nearby, and your brain estimates size by comparing familiar references. In the night sky, those references disappear. Stars offer no scale markers, no overlapping edges, no shadows that suggest depth. What remains is angle, the simplest and most honest measurement available from a single viewpoint. Angle describes how far apart two objects appear from where you stand. When you look at Orion's belt, the stars seem close because the angle between them is small. If they were spread farther across the sky, the angle would increase, even if the stars themselves had not moved. This idea may feel abstract, yet it mirrors daily experience. Two distant streetlights may appear close together when viewed from far away, while the same lights look widely separated when you stand beneath them. Astronomy relies on this geometric truth. The sky becomes a sphere surrounding Earth, and positions are mapped using degrees, minutes, and seconds of arc. 1 degree is a small slice of the sky, about the width of your little finger held at arm's length. Each degree divides into 60 arc minutes, and each arc minute divides into 60 arc seconds. These units allow precise descriptions of where stars appear, even when their true distances remain unknown. When you hear that Orion spans more than 20 degrees from top to bottom, you are hearing about apparent size, not physical extent. Apparent size depends entirely on perspective. The moon, for example, spans about half a degree in the sky, yet its actual diameter is over 3,000 kilometers. The Sun appears nearly the same size, even though it is vastly larger, because it lies much farther away. This coincidence teaches an important lesson. Angle alone cannot reveal true size without distance. To move from angles to physical dimensions, astronomers need a second ingredient. Distance allows angles to become lengths. If you know how far away something is, a small angle can translate into a massive structure. Without distance, angles remain shapes drawn on the sky, informative but incomplete. Orion, as you see it, is a collection of angles waiting for depth. Perspective governs all of this. On Earth, perspective changes as you move. Nearby objects shift position against distant backgrounds. This effect is subtle for stars, because even the closest ones are far beyond ordinary experience. Still, the principle remains. A change in viewpoint reveals depth through motion, even when that motion is small. You can sense this by closing one eye and then the other. Nearby objects jump slightly, while distant mountains barely shift. Your brain uses this difference to infer distance. In astronomy, Earth's motion around the Sun provides a similar change in viewpoint, though spread across millions of kilometers and measured with delicate instruments. The shift is tiny, but it exists. Brightness adds another layer. Light spreads as it travels, weakening with distance according to well-tested physical laws. A star twice as far away appears 4 times dimmer if all else is equal. This inverse relationship offers clues, but only when combined with knowledge of how much light a star produces. Without that, brightness can mislead, making distant luminous stars appear deceptively close. As you observe Orion, your eyes integrate angle and brightness unconsciously. The result feels immediate and confident, even though it lacks depth. Science slows this process down, separating appearance into measurable parts. Angles are recorded carefully. Brightness is quantified. Spectra reveal temperature and composition. Each measurement removes a little ambiguity without rushing the mind. The calm power of angular measurement lies in its stability. Angles do not depend on assumptions about a star's nature. They are direct observations, repeatable and precise. Long before distances were known, astronomers mapped the sky accurately using angles alone. Those maps remain useful today, layered with modern data that add depth without erasing the original framework. When you think of the sky as a coordinate system rather than a ceiling, its structure changes gently in your imagination. Orion's outline remains familiar, but it becomes a projection, like a shadow cast by a three-dimensional arrangement. The stars are no longer imagined as equally distant points, but as objects aligned by chance along your line of sight. This understanding does not require effort. It settles naturally as you continue to look upward. The belt stars still form a straight line. The shoulders still mark a broad span. Yet beneath this calm picture lies a deeper geometry, one that waits patiently for distance to give it form. As night deepens, the idea of measurement replaces the illusion of flatness. Angles become the language that connects your eyes to vast scales. They are the first step in turning the sky from a pattern into a structure. With angles established, the remaining question rests quietly in your thoughts. How far away are these lights, and how does that distance reshape everything you see? This question has guided careful observation for centuries. Each clear night adds more data, even when it feels still. Stars drift slightly across the sky over years, revealing motion relative to one another. Some shifts arise from Earth's own movement, others from the stars traveling through space. These motions are slow, but they are real, and they provide another layer of measurable perspective. You remain grounded beneath the atmosphere, aware that the air itself bends light slightly, altering apparent positions by small amounts. Astronomers account for this, correcting observations so angles reflect space rather than air. This attention to detail ensures that what seems calm and simple to the eye becomes precise and reliable in measurement. As you rest with these ideas, the sky feels less like a mystery and more like a carefully observed environment. Angles, brightness, and motion work together, each offering partial insight. None rush toward conclusions. They wait to be combined, step by step, into a fuller understanding of scale that extends gently beyond the limits of sight. The calm realization settles that distance is the missing dimension, quiet but essential. Once it is known, angles gain weight and shapes gain volume. Until then, the sky remains a precise outline, inviting depth to reveal itself through patient measurement in time ahead. You begin by letting the idea of distance settle gently, allowing it to stretch beyond everyday experience without resistance. On Earth, distance is measured in steps, meters, or kilometers. These units work because light arrives almost instantly, making space feel small and immediate. In astronomy, that immediacy disappears. Light itself becomes the ruler, not because it is abstract, but because it is the fastest and most reliable signal available. Light travels at a constant speed in a vacuum, measured carefully and repeatedly as approximately 300,000 kilometers per second. This value is not an estimate or approximation. It has been confirmed through laboratory experiments, astronomical observation, and modern technology. Because light speed is constant, it provides a dependable way to translate time into distance, forming the basis of the light year. A light year is the distance light travels in 1 year, moving uninterrupted through empty space. It equals about 9.5 trillion kilometers. This number is precise, yet saying it aloud rarely creates understanding. Instead, the light year works because it connects distance to something familiar, time. You already understand how long a year feels. The light year simply asks you to imagine light moving continuously for that duration, without slowing, turning, or stopping. This unit does not imply that time itself stretches or that the stars exist in the past in any unusual sense. It only describes how far away something is. When light leaves a star and travels toward Earth, it carries information about that star's condition at the moment of emission. The delay does not distort reality. It reflects the finite speed at which information moves through space. As you look at Orion, each star sends light that has been traveling for years before reaching your eyes. Some stars are hundreds of light years away, meaning their light began its journey long before you noticed it. This does not mean the stars are frozen in history. They continue to exist and change, but what you observe is always a slightly earlier version, arriving steadily and predictably. This idea feels subtle rather than dramatic. The delay is constant and unavoidable, not mysterious. It applies to everything you see, from nearby planets to distant galaxies. Even sunlight takes about 8 minutes to reach Earth. The difference with stars lies only in scale, not in principle. Using light years allows astronomers to work comfortably with distances that would otherwise require unwieldy numbers. Instead of saying trillions of kilometers repeatedly, they refer to a few hundred light years and remain precise. The unit simplifies communication without reducing accuracy. You may notice that the term includes the word year, which can suggest time rather than distance. This confusion fades once the definition becomes familiar. A light year is not how long light travels, but how far it goes during a known interval. The interval provides scale, not meaning. In Orion, the stars you see are not equally distant. Some lie roughly 400 light years away, others more than 1,000. These differences are invisible to the eye, yet they define the constellation's true shape. The belt stars appear aligned, but they sit at different depths, separated by hundreds of light years along your line of sight. Light carries more than brightness. It carries color, which reveals temperature, motion, and composition. These properties remain intact across light years of travel. Space is thin enough that light rarely collides with anything, allowing it to move in straight lines over vast distances. This reliability is why astronomy is possible at all. As you rest with this knowledge, the sky begins to feel layered rather than distant. Light years do not push stars away emotionally. They place them accurately. Each measurement anchors the sky in physical reality, replacing vague immensity with defined separation. Distance no longer feels like emptiness. It becomes a medium through which light moves steadily, connecting stars to observers through measurable paths. The calm certainty of this connection allows your thoughts to settle rather than drift. Understanding light years gently prepares you to think in 3 dimensions. The sky is no longer a surface but a volume filled with objects at different ranges. Each star occupies a specific location, defined by coordinates and distance, not by appearance alone. This realization does not require effort. It unfolds naturally as your mind adjusts to scale. The vastness remains, but it becomes organized rather than overwhelming. Light years transform space into something navigable, even when it remains far beyond physical reach. As you continue to observe Orion, the stars remain steady, their light arriving faithfully across time and distance. The knowledge that each point of light has traveled a known length through space adds quiet depth to the view. Distance, once abstract, now rests on a constant speed and a measured interval, forming a bridge between where you stand and where the stars truly are. You continue to rest your attention on Orion, allowing the familiar outline to remain steady while your understanding slowly shifts beneath it. The stars still appear arranged in a single plane, but measured distance begins to loosen that illusion. Each point of light occupies its own location in space, separated from the others not by small gaps, but by spans measured in hundreds of light years. When astronomers determine distances to Orion's stars, a striking fact emerges. The constellation is not a cluster or a unified structure. Its stars do not form a group moving together through space. Instead, they lie along similar lines of sight from Earth, aligned by perspective rather than proximity. The shape you recognize exists only from this one vantage point. Some of Orion's brightest stars are relatively nearby by stellar standards. Others are much farther away, yet appear equally prominent because of their intrinsic luminosity. This variation produces a wide depth, like beads scattered along a long thread, all appearing close together when viewed from one end. Your eyes compress this depth into a flat image because light carries no built-in distance marker. Betelgeuse, for example, lies roughly several hundred light-years from Earth. Rigel, though nearby in the sky, is significantly farther away. The belt stars occupy different ranges as well, spread across vast distances that cannot be sensed without measurement. When these separations are visualized accurately, the familiar outline stretches into a long, uneven structure extending deep into space. This depth is not speculative. It comes from repeated observations, refined instruments, and cross-checked methods. Parallax measurements, brightness analysis, and spectral data all contribute to determining where each star truly resides. Each method has limits, but together they build a consistent picture that confirms Orion's three-dimensional nature. Your brain naturally prefers simplicity. A flat pattern is easy to hold and remember. Depth requires effort, especially when the distances involved exceed ordinary experience. Astronomy respects this limitation and works around it, translating depth into numbers that can be compared calmly and clearly. When these distances are plotted, Orion becomes less like a drawing and more like a scattered region of space. The stars do not form a wall or a sheet. They occupy different depths, some closer to Earth, others farther, each moving independently through the galaxy. Over millions of years, the pattern itself will change as these motions accumulate. This change is slow enough to feel almost eternal, yet it is real and measurable. Proper motion, the gradual shift of stars across the sky, reveals that constellations are temporary arrangements. Orion's current shape is a momentary alignment on cosmic timescales. The depth you are learning about ensures that this alignment cannot last forever. Understanding this does not diminish the pattern's usefulness. Orion remains a reliable guide for observation and orientation. The knowledge of depth simply adds accuracy beneath the surface, allowing you to hold two truths at once. The pattern is visually real, and its physical structure is far more complex. As you imagine Orion extending away from you, the sky begins to feel spacious rather than distant. Depth transforms emptiness into volume. Space is no longer a void behind the stars, but the very medium in which they exist, measured and defined by their separation. The distances between Orion's stars are not small gaps. They are vast regions of space filled with thin gas, magnetic fields, and occasional dust. Light crosses these regions with little interference, preserving the appearance of closeness even when true separation is immense. This quiet transparency is what allows depth to remain hidden. Modern star catalogs list precise distances for thousands of stars in Orion's direction. Each entry represents years of observation and careful analysis. When these data are combined, the constellation dissolves into a loose arrangement of objects, each with its own story, age, and motion. This understanding replaces the idea of Orion as a single thing with a more accurate view. Orion is a direction, not a destination. It is a window through which you observe stars at many different ranges. The name remains convenient, but the science reveals what convenience conceals. As you rest with this idea, the sky feels less like a map and more like a landscape viewed from afar. The depth does not rush forward. It remains implied, waiting to be noticed through measurement rather than sensation. This quiet waiting matches the slow pace of observation itself. You may sense that depth introduces complexity without confusion. It does not tangle the view. It enriches it. Each star's position becomes more meaningful once it is placed in three-dimensional space. Distance adds context to brightness, color, and motion. This context allows astronomers to ask better questions. Which stars formed together, and which are merely aligned? Which share similar ages or origins, and which arrived from different regions of the galaxy? Depth makes these questions possible by separating coincidence from connection. As Orion remains overhead, unchanged in appearance, your understanding gently deepens. The constellation no longer feels like a single object but like a layered region extending far beyond the limits of sight. This layered reality rests quietly beneath the familiar outline, stable and well-measured. The realization settles that seeing is only the beginning. The sky offers patterns, but measurement reveals structure. Depth, once invisible, becomes an essential dimension, allowing size to be defined not by appearance, but by separation through space. This awareness prepares the mind to appreciate how such distances are measured with increasing precision, using Earth's own motion as a subtle tool. You remain grounded beneath the sky, aware now that distance is the missing dimension that gives shape to everything you see. To uncover that distance, astronomy relies on a subtle effect that requires patience, precision, and motion. This effect is called parallax, and it arises not from the stars themselves, but from your changing position as Earth moves through space. Parallax is the apparent shift of an object against a more distant background when the observer's position changes. You experience it easily in daily life. Hold a finger in front of your face and alternate closing one eye and then the other. Your finger seems to jump sideways, while distant objects remain fixed. The size of that jump depends on how close your finger is. This simple geometry forms the foundation of stellar distance measurement. In astronomy, the baseline is much larger. Instead of the distance between your eyes, the baseline becomes the diameter of Earth's orbit around the Sun. As Earth moves from one side of its orbit to the other over 6 months, nearby stars appear to shift slightly against the background of much more distant stars. This shift is extremely small, often less than a single arcsecond, yet it is measurable with careful observation. The geometry is straightforward. If you know the size of the baseline and measure the angle of the shift, you can calculate the distance using trigonometry. No assumptions about a star's brightness or behavior are required. Parallax depends only on position and motion, making it one of the most direct and reliable methods in astronomy. When parallax was first proposed, the expected shifts were beyond the reach of available instruments. Early astronomers searched for them unsuccessfully, not because the idea was wrong, but because the stars were farther away than anyone had imagined. The absence of detectable parallax became early evidence that the universe extended far beyond the solar system. Eventually, improvements in telescopes and measurement techniques allowed parallax to be detected. The first successful stellar parallax measurements in the 19th century confirmed that stars lay at immense distances. This moment transformed astronomy from a descriptive science into a quantitative one, anchoring the sky in measurable space. Parallax works best for nearby stars. As distance increases, the apparent shift becomes smaller, eventually blending into measurement uncertainty. Beyond a few thousand light-years, parallax from Earth's orbit becomes too small to detect reliably with ground-based instruments. This limitation is not a weakness, but a boundary that defines where other methods must take over. In the region of Orion, parallax plays a crucial role for the nearer stars. Measurements reveal that even stars appearing side by side in the sky can have noticeably different parallaxes, confirming their separation in depth. These differences are small in angle, yet large in physical distance, reinforcing how deceptive appearance can be without measurement. The units used in parallax reflect its geometry. A star with a parallax of 1 arcsecond lies at a distance of 1 parsec, equal to about 3.26 light-years. Most stars have parallaxes far smaller than 1 arcsecond, requiring precision that borders on the limits of instrumentation. Each successful measurement represents years of refinement and calibration. Atmospheric turbulence complicates ground-based parallax measurements by blurring stellar positions. Astronomers account for this by averaging many observations and correcting for known effects. Even so, Earth's atmosphere sets a practical limit on precision, encouraging the development of space-based observatories. Despite these challenges, parallax remains the foundation upon which other distance methods are built. It provides the first rung of the distance ladder, a set of directly measured distances that calibrate indirect techniques. Without parallax, estimates of stellar brightness, size, and energy output would lack a reliable scale. As you consider Orion again, parallax adds quiet confidence to what you have learned. The depth across the constellation is no longer inferred indirectly. It is measured through Earth's own movement, using geometry that holds regardless of scale. The motion of the planet becomes part of the observation, linking your position to the stars. This connection feels grounding rather than abstract. Earth is not isolated beneath the sky. It participates in the measurement of the universe. Each orbit traces a path that reveals depth, one small angle at a time. The stars respond not by moving, but by revealing their distance through relative shift. Parallax also teaches restraint. It reminds astronomers that not all distances can be measured directly from a single method. Where parallax fades, other approaches must be carefully calibrated against it. This layered strategy preserves accuracy while extending reach. You may notice that parallax does not rely on brightness or color. It treats stars as points in space, stripped of personality or variability. This simplicity is its strength. It measures position alone, leaving interpretation to follow once distance is secure. As the night remains still, Earth continues its orbit, carrying observers along a path that silently measures the sky. Parallax works whether or not it is noticed, its geometry unfolding steadily with time. The effect is always present, waiting for instruments precise enough to capture it. With parallax, distance becomes something earned through motion and patience. It is not guessed or imagined, but calculated from observable shifts. This reliability gives weight to every subsequent measurement, anchoring the vast scales of Orion in a framework that begins beneath your feet. The calm certainty of this method prepares your thoughts for tools that extend even farther, using space itself as an observing platform. As measurement grows more precise, the depth of Orion becomes clearer, defined not by appearance, but by angles traced across Earth's quiet path around the Sun. You remain with the idea of distance, now supported by careful geometry, and allow it to expand gently into a new scale of measurement. Earth's orbit provides a useful baseline, but its atmosphere places limits on precision. Air bends light, shifts positions, and introduces subtle noise. To move beyond those limits, observation must leave the surface entirely. This is where space-based measurement becomes essential. The Gaia spacecraft operates far above the atmosphere, orbiting the Sun along with Earth. From this stable vantage point, it observes the sky without distortion from air or weather. Gaia does not take pictures in the familiar sense. Instead, it measures positions, brightness, and motion of stars repeatedly, building precision through repetition and time. Gaia's primary task is astrometry, the measurement of stellar positions and movements. It observes each star many times over years, tracking tiny changes in position caused by parallax and proper motion. These changes are minute, often measured in microarcseconds, far smaller than what ground-based telescopes can reliably detect. This level of precision allows distances to be determined for stars thousands of light-years away. Parallax angles too small to measure from Earth become detectable from space. The result is a three-dimensional map of the Milky Way that is both vast and detailed, grounded in direct observation rather than inference. In the direction of Orion, Gaia reveals a complex structure. Stars once grouped only by appearance separate into layers at different depths. Some lie relatively close, others far beyond, each with a measured position in space. The familiar outline dissolves into a cloud of points, each one precisely located. Gaia also measures proper motion, the slow movement of stars across the sky relative to distant backgrounds. Combined with distance, this motion reveals how stars travel through the galaxy. In Orion's region, this information shows that many stars share no common origin, moving independently despite their apparent proximity. Measurement uncertainty plays an important role here. Gaia does not provide a single number without context. Each distance comes with an uncertainty range that reflects observational limits. These ranges are small compared to earlier methods, yet they are acknowledged openly. Precision improves understanding not by claiming perfection, but by defining confidence. This approach allows astronomers to refine models gradually. As more data accumulate, uncertainties shrink, patterns sharpen, and relationships emerge. Orion's depth becomes clearer not all at once, but through steady improvement. This patience mirrors the slow rhythm of observation itself. Gaia's data confirm that Orion spans hundreds of light-years in depth. Some stars in its direction belong to nearby regions of star formation, while others are distant giants shining across great separations. The constellation's apparent unity gives way to a structured volume of space. You may notice that this transformation does not erase the sky you see. Orion remains recognizable, its stars still forming familiar lines. The difference lies beneath the surface, where precise numbers replace assumptions. The outline remains useful, but it no longer defines reality on its own. The scale of Gaia's work is difficult to grasp, yet its method remains simple at heart. Measure positions repeatedly. Track motion carefully. Let geometry reveal distance. This simplicity, applied with extreme precision, produces a map of extraordinary reach. As you rest with this idea, the sky feels quietly organized. Each star has coordinates, motion, and distance, all derived from observation. The vastness remains, but it is no longer vague. It is structured, measured, and described with care. Gaia also reveals groups within Orion's direction that do share origins. Clusters and associations emerge once depth is known. These groups are physically connected, formed from the same clouds of gas. Distinguishing them from chance alignments becomes possible only with three-dimensional data. This distinction matters because it changes how size is understood. Orion is not one object, but it contains real structures embedded within its outline. Some are compact and connected, others widely separated. Size becomes layered depending on what is being measured. The calm power of Gaia's contribution lies in clarity rather than drama. There is no sudden revelation, only gradual refinement. Each data release sharpens the picture, reducing uncertainty and improving scale. The sky becomes less mysterious without becoming less vast. You may sense that this precision does not distance you from the stars. Instead, it brings them into clearer relationship with where you stand. Earth's motion, combined with Gaia's vantage point, forms a measuring system that spans space calmly and reliably. As the data accumulate, Orion's stars settle into their true positions, no longer flattened by perspective alone. Depth, motion, and distance work together, revealing a region of space that is extended, varied, and well-defined. This understanding prepares your thoughts to focus on individual stars within Orion, not as points of light, but as physical objects with measurable size, mass, and energy output. The map is now in place, quiet and precise, allowing attention to rest on what occupies it. You let your attention settle on two lights that define Orion's presence in the sky. One glows with a warm, reddish tone, steady and noticeable even without effort. The other shines sharply white-blue, crisp and intense. These are Betelgeuse and Rigel, among the most studied stars visible from Earth. Though they appear similar in prominence, their physical nature could not be more different. Betelgeuse is a red supergiant star. Its color comes from a relatively cool surface temperature, measured at a few thousand degrees. Cool, in stellar terms, still means hot enough to emit enormous amounts of energy. The redness does not imply weakness, but a different stage of stellar life, one governed by known nuclear processes. The size of Betelgeuse is difficult to imagine without careful framing. Its radius is hundreds of times larger than that of the Sun. If it were placed at the center of the solar system, its outer layers would extend beyond the orbit of Mars. This comparison is not metaphorical. It comes directly from measured angular size and distance, combined through geometry. Despite its immense size, Betelgeuse is not extremely dense. Its outer layers are diffuse, meaning matter is spread thinly across a vast volume. This structure arises naturally as massive stars exhaust the hydrogen fuel in their cores and begin fusing heavier elements. The expansion follows well-tested models of stellar evolution. Rigel, by contrast, is a blue supergiant. Its surface temperature is much higher than Betelgeuse's, giving it a bright blue-white color. Though smaller in radius than Betelgeuse, Rigel is still far larger than the Sun and vastly more luminous. Temperature plays a critical role here. Hotter surfaces emit much more energy per unit area, a relationship described precisely by physics. Luminosity measures how much energy a star emits each second. Rigel's luminosity exceeds that of the Sun by tens of thousands of times. This is not inferred from appearance alone, but calculated using distance and observed brightness. Once distance is known, apparent brightness becomes a direct window into energy output. These stars illustrate why brightness can mislead. Betelgeuse appears very bright partly because it is relatively closer than Rigel. Rigel appears equally bright because it emits far more energy. Your eyes register similar intensity, but the underlying causes differ profoundly. Mass adds another layer of scale. Both Betelgeuse and Rigel are far more massive than the Sun, containing many times its material. Mass determines how quickly a star burns its fuel and how it will eventually end its life. These relationships are supported by observation of many stars at different stages, forming a consistent pattern across the galaxy. The Sun, by comparison, is modest. It is stable, middle-aged, and average in mass and size. Using it as a reference helps ground stellar scale. When you hear that Betelgeuse's radius is hundreds of solar radii, or that Rigel's luminosity is tens of thousands of solar luminosities, the comparison anchors abstraction to something known. These measurements come from multiple methods. Spectroscopy reveals temperature and composition. Distance allows size and luminosity to be calculated. Models of stellar interiors explain how mass, pressure, and fusion interact. None of these elements stands alone. Each supports the others through consistency. Stellar size is not a surface you could stand on. Stars have no solid boundary. Their edges are defined by where gas becomes thin enough to stop emitting light effectively. This makes size a measured property rather than a tangible surface, yet it remains precise and repeatable. When you look at Orion now, the stars no longer feel interchangeable. Each one represents a different balance of mass, temperature, and stage of life. Betelgeuse is nearing the end of its stable existence, having expanded as its internal fuel changes. Rigel remains in a different phase, burning intensely and steadily for now. This knowledge does not introduce urgency. Stellar lifetimes, even in late stages, span tens of thousands to millions of years. Changes occur far too slowly to disrupt the calm of observation. The stars remain steady lights, their internal processes unfolding quietly. Scale at this level becomes layered. Distance tells you how far away a star is. Size tells you how large it is. Luminosity tells you how much energy it produces. None of these can be inferred reliably from sight alone. They require measurement, patience, and cross-checking. As you rest with these ideas, the stars feel more substantial without becoming less serene. They are not symbols or abstractions, but physical objects governed by the same laws everywhere. Hydrogen fuses into helium. Energy moves outward. Gravity holds matter together. These processes repeat across the galaxy. The clarity of this understanding allows wonder to remain grounded. Betelgeuse and Rigel are extraordinary, not because they are imagined as dramatic, but because their measured properties stretch scale far beyond daily experience. Their reality is enough. With these stars in mind, Orion becomes more than a pattern of points. It becomes a region populated by objects of vastly different sizes and energies. Some dominate space through sheer volume, others through intensity. Each contributes to the overall scale of what you are seeing. This awareness prepares your thoughts to expand outward again, beyond individual stars, toward the regions of gas and dust that surround them. Size will soon apply not just to stars, but to the vast structures in which stars are born, extending Orion's scale even further into space. You allow your attention to move beyond individual stars and rest instead on the space between them. What once seemed empty begins to take on structure. In the direction of Orion, this structure is extensive, measured, and well observed. It is known as the Orion Molecular Cloud Complex, one of the nearest large regions of star-forming material to Earth. This complex is not visible in the same way stars are. To the unaided eye, it appears as darkness or faint haze, because its material does not emit much visible light. Instead, it absorbs and scatters it. The cloud is composed primarily of molecular hydrogen, along with helium and trace amounts of heavier elements and dust. These ingredients are thinly spread, yet together they occupy an enormous volume of space. Molecular hydrogen is difficult to detect directly because it does not emit strongly at the temperatures found in these clouds. Astronomers therefore rely on indirect tracers. Carbon monoxide, present in small amounts, emits radio waves that pass easily through dust. By observing these emissions with radio telescopes, scientists map the cloud structure with precision. Infrared observations add another layer. Dust grains warmed slightly by nearby stars emit infrared radiation. This light penetrates regions that visible light cannot, revealing dense knots and filaments within the cloud. Together, radio and infrared data transform what looks like darkness into a detailed, three-dimensional structure. When these observations are combined with distance measurements, the scale becomes clear. The Orion Molecular Cloud Complex stretches hundreds of light-years across. It is not a single object but a collection of connected regions, each with its own density and activity. Some parts are actively forming stars, while others remain relatively quiet, holding their material in reserve. This size is not inferred loosely. It is calculated by measuring angular extent on the sky and converting that angle using known distances. Once depth is included, the cloud becomes a vast volume rather than a flat patch. Its mass is estimated to be hundreds of thousands of times that of the Sun, spread thinly across space. Within this cloud, gravity plays a slow and steady role. Most of the time, gas pressure and internal motion counteract gravitational collapse. Only in regions where density becomes slightly higher does gravity begin to dominate. These regions contract gradually, cooling as energy radiates away, allowing collapse to continue. Star formation is not sudden. It unfolds over millions of years. As a dense core contracts, temperature and pressure rise at its center. When conditions become extreme enough, nuclear fusion begins, and a new star forms. This process follows physical laws tested both in observation and in laboratory physics. The Orion Molecular Cloud Complex contains many such cores at different stages. Some are just beginning to condense. Others already host young stars still surrounded by disks of gas and dust. These disks are detected through infrared excess, a clear observational signature of material warmed by a central object. Despite its immense size, the cloud is remarkably calm on human timescales. Motions within it are slow, measured in kilometers per second, negligible compared to the distances involved. This slow pace contributes to the steady rhythm of star formation, preventing rapid collapse and allowing structures to persist. You may notice that this calm contrasts with the dramatic imagery often associated with star formation. In reality, the process is governed by balance. Gravity pulls inward. Pressure, magnetic fields, and turbulence push outward. The result is gradual change rather than sudden transformation. The cloud's presence also affects how Orion's stars are distributed. Many of the stars you see formed from this same reservoir of material, though at different times and in different places. Others, aligned by chance along your line of sight, have no physical connection to the cloud at all. Depth once again separates coincidence from relationship. Because the cloud absorbs visible light, it creates dark lanes and patches against brighter backgrounds. These features were noted long before their nature was understood. Today, they are recognized as dense regions where dust blocks starlight, providing clear evidence of material between stars. The study of such clouds is not limited to Orion. Similar structures exist throughout the Milky Way. Orion's proximity makes it especially valuable, allowing details to be observed that are blurred in more distant regions. What is learned here applies broadly, forming part of a consistent picture of how stars form across the galaxy. As you consider the cloud scale, individual stars begin to feel like small features within a larger environment. Even supergiant stars occupy tiny fractions of the cloud's volume. Size, once centered on stellar dimensions, now expands to encompass regions that dwarf entire planetary systems. This expansion does not overwhelm the mind. It unfolds gently, grounded in measurement. Hundreds of light-years are large, but they are defined, mapped, and understood. The cloud's boundaries are not sharp, but its extent is measurable within known uncertainty. The Orion molecular cloud complex also reminds you that space is not empty. Even regions considered dense by interstellar standards are far more rarefied than any vacuum created on Earth. Yet over vast volumes, this thin material accumulates into structures capable of forming stars and planets. As you rest with this idea, the sky feels quietly full. Between the stars lies matter, structured and dynamic, shaped by forces that operate everywhere. The cloud does not demand attention visually, yet it defines much of what Orion truly is. Understanding this shifts scale once more. Orion is no longer just a collection of stars or a pattern on the sky. It is part of a much larger physical system, where gas, dust, gravity, and time interact. This awareness invites reflection on regions where individual stars are still emerging, glowing within the surrounding material, measured carefully through the light they influence rather than emit. Your attention moves now to a brighter, more compact region within the larger cloud, known as the Orion Nebula. Unlike the surrounding molecular cloud, this nebula emits visible light, allowing it to be observed directly. Its glow is caused not by reflected sunlight, but by emission, a physical process in which atoms release energy as light when excited. The nebula is composed primarily of hydrogen gas. Ultraviolet radiation from young, massive stars excites the surrounding hydrogen atoms, stripping electrons from protons in a process called ionization. As electrons recombine with protons, energy is released in the form of photons, producing the characteristic pinkish-red glow visible in images. This process follows precisely the laws of atomic physics and electromagnetism, confirmed in laboratories and through repeated observation. Observing the nebula in multiple wavelengths provides complementary information. Radio waves trace cold gas, revealing regions still dense and unlit. Infrared detects dust warmed by embedded stars, penetrating the opaque layers of the cloud. Optical observations capture the emission from ionized gas, showing both structure and energy output. Together, these measurements create a layered map of the region. The size of the nebula is well established. Its diameter spans roughly 20 to 24 light-years. Astronomers determine this by measuring angular size on the sky and applying the distance previously determined through parallax and other methods. The result is a defined physical scale, translating apparent size into measurable dimensions. Mass is another measurable property. Using the density of hydrogen and the volume derived from observed dimensions, scientists estimate the nebula's mass at several thousand times that of the Sun. This mass is concentrated within clumps and filaments, where gravity can overcome pressure to form stars. The distribution is uneven, creating both dense stellar nurseries and more diffuse regions. Within the nebula, new stars are actively forming. Dense cores collapse under gravity, heating as contraction continues. Once the central temperature is sufficient, nuclear fusion ignites, marking the birth of a star. Young stars are often surrounded by disks of gas and dust, detected as infrared excess due to heating by the central object. Observations confirm that these protoplanetary disks are common, providing the raw material for potential planetary systems. Stellar winds from young, massive stars shape the nebula's structure. High-energy particles push gas outward, creating cavities and filaments. Radiation pressure contributes to sculpting the cloud, while gravity acts on denser clumps. The interplay of these forces is gradual but measurable, producing dynamic yet stable features over thousands of years. Emission lines from hydrogen and other elements allow astronomers to calculate temperature and density within the nebula. Hydrogen's emission produces the strong H-alpha line, visible in optical telescopes. Additional lines from oxygen, sulfur, and nitrogen provide further diagnostic tools. These observations are precise, repeatable, and entirely consistent with the physics of ionized gases. The Orion Nebula is also a laboratory for measuring stellar energy transfer. Light from massive stars heats surrounding gas and dust, which re-emits energy at longer wavelengths. This energy flow is predictable according to radiative transfer equations. Observed brightness and spectra match theoretical calculations closely, demonstrating the reliability of physical laws across vast distances. Distance measurements place the nebula at approximately 1,350 light-years from Earth. Combining angular size with distance allows accurate determination of diameter, while radio and infrared mapping reveal substructures within. The resulting three-dimensional picture shows dense clumps, cavities carved by stellar winds, and extended filaments stretching for dozens of light-years. Despite its activity, the nebula remains calm to the observer's eye. Changes unfold over thousands of years, far longer than a single night. This slow evolution allows measurement to proceed methodically, confirming models of star formation and gas dynamics without haste. The nebula is luminous, yet stable in a long-term sense. By observing multiple stars within the nebula, astronomers identify clusters of young objects with shared origins. Their motions are consistent with formation from the same cloud material, confirming theories of clustered star formation. These clusters illuminate the processes that build stellar populations across the galaxy. The nebula's physical properties are not guesses. They are determined through calibrated instruments, repeated measurements, and well-understood physics. Every detail, from mass to temperature to composition, is derived from observable phenomena. This approach ensures that Orion's structure is understood quantitatively, not symbolically. Light itself provides direct information. Spectral lines reveal chemical composition and ionization states, while Doppler shifts measure motion along the line of sight. Combined with proper motion data, the three-dimensional movement of stars and gas becomes clear. This motion contributes to the nebula's evolution and eventual dispersal over millions of years. The Orion Nebula sits within the larger molecular cloud, linking individual stars to extended interstellar material. Its size is smaller than the full cloud, yet it contains enough mass to form thousands of stars over time. The nebula illustrates how gas and dust transition into luminous objects, connecting scales from clouds to individual stars. You may notice that the nebula is not uniform. Bright regions indicate dense, highly ionized areas, while fainter zones mark lower density or obscured material. This variation is expected and measurable, arising from physical laws rather than arbitrary distribution. Observations across wavelengths confirm the presence of cold, dense cores hidden within glowing regions. Even the faintest features can be quantified. Filaments and cavities are mapped with radio telescopes, while dust temperature is inferred from infrared emission. These measurements provide a complete physical picture, showing how matter is organized and how energy flows through the region. The nebula becomes an extended laboratory for observing ongoing stellar formation. By defining diameter, mass, structure, and motion, astronomers transform the Orion Nebula from a bright patch in the sky into a detailed, three-dimensional object. Its scale, measured precisely, offers perspective on the larger cloud complex, showing how individual stars relate to the interstellar medium that surrounds them. The calm clarity of these observations allows the mind to appreciate scale without urgency. The nebula is both enormous and well-defined, luminous and structured. Its activity proceeds according to known physics, measured through the light it emits, absorbed, and re-radiated. As you rest with these ideas, Orion's pattern begins to feel layered and coherent. Individual stars, the molecular cloud, and the nebula itself now exist as defined regions with measurable size, mass, and motion. This understanding gently prepares your thoughts to consider how these scales compare to the solar system, where distances, empty space, and relative size offer a different perspective on vastness and proportion. You let your thoughts shift inward for a moment, toward the familiar scale of the solar system, while still observing Orion in the sky. The comparison is not intended to shrink Orion, but to provide perspective on size, distance, and proportion. Even the closest stars are far larger and farther apart than any planet or orbit you experience. Begin with distances. The Earth orbits the Sun at roughly 150 million kilometers, or 1 astronomical unit. Neptune, the outermost planet, lies about 30 times farther. These numbers are enormous by daily standards, yet they are small compared to interstellar separations. The nearest stars in Orion's belt, for example, lie hundreds of light-years away. 1 light-year equals about 63,000 times the distance from Earth to the Sun. The gap between planets and stars is therefore staggeringly greater than any scale within the solar system. Because numbers grow so large, logarithmic thinking is helpful. Instead of adding or subtracting distances linearly, you consider orders of magnitude. 1 light-year, 10 light-years, 100 light-years. Each step represents a tenfold change. This approach allows you to hold multiple scales in your mind without confusion, seeing planetary orbits and star separations together without distortion. Empty space dominates all of these scales. Within the solar system, planets occupy tiny fractions of the volume. Between stars, matter is spread so thinly that even the densest clouds contain less material per cubic meter than the best laboratory vacuum on Earth. Orion's molecular cloud, while enormous in mass, is mostly space. The stars embedded within it are tiny in comparison to the volume they occupy. Physical size also differs greatly. Betelgeuse, a red supergiant in Orion, is hundreds of times the radius of the Sun. A single star can outsize the entire planetary system many times over. Yet even a star occupies an almost negligible fraction of the space between stars. Distances dominate perception and measurement at this scale. Orion's nebula, about 20 light-years across, dwarfs the solar system. The Sun's outer planets orbit within a distance of less than 1 trillion kilometers, less than a light day. Even the nearest gas clouds in Orion are separated by tens to hundreds of light-years. These differences underscore the challenge of comprehension. Objects themselves can be enormous, yet space between them is even more immense. The comparison also highlights why visual appearance can mislead. Stars appear as points of light, their sizes reduced to angular dimensions in the sky. Planets appear similarly small when viewed without telescopes. In both cases, perception underestimates physical scale. The solar system teaches the same lesson on a smaller stage. The Sun dominates gravitationally, but most volume remains empty. To grasp these scales more calmly, you can think in ratios. The diameter of the Orion Nebula relative to the solar system is comparable to a single orbit compared to the distance across a city. Distances between stars in Orion are then thousands of times larger than that. Considering ratios rather than raw numbers keeps understanding precise without overwhelming the mind. Motion also differs across scales. Planets orbit the Sun in years to centuries. Stars move through space at tens to hundreds of kilometers per second, but their apparent shift in the sky is slow due to the immense distances. Orion's stars and clouds drift gradually relative to one another, their motion traceable over decades and centuries, yet imperceptible during a single night. This perspective clarifies how structures form. Within the solar system, gravity dominates locally. Between stars, gravitational influence is weaker over vast distances, but accumulates within clouds and clusters to shape star formation. The empty space separating stars does not preclude structure. It sets the context in which structure emerges. Understanding the emptiness between stars also reveals why measurement matters. Without knowing distance, size, or scale, the sky can only be appreciated visually. Adding numbers transforms perception into understanding. The solar system provides a comfortable reference, allowing the mind to extend its intuition to the larger, emptier scales of Orion. Even within the Orion molecular cloud, density is low. Individual stars occupy tiny volumes, with vast space separating them. The nebula itself, while bright and structured, is mostly gas spread thinly. This reinforces the principle that cosmic size is measured not just by objects, but by the space they occupy and influence. Logarithmic thinking is useful for comparing energy output as well. Betelgeuse shines tens of thousands of times more brightly than the sun. Rigel exceeds that by additional factors. Luminosity scales far faster than physical size, yet energy per unit area follows known laws. Recognizing these scales alongside spatial scales adds depth without confusion. By reflecting on these comparisons, you notice how Orion is nested within larger structures. Individual stars relate to clouds. Clouds relate to clusters. Clusters relate to the galaxy. The hierarchy of scale is calm and continuous, measured rather than imagined. The solar system is the first step in this chain, providing a grounded reference for enormous distances beyond. This exercise also reinforces patience. Grasping logarithmic differences allows the mind to adjust gradually. You do not need to visualize each light year as a linear stretch. Instead, you acknowledge orders of magnitude and let understanding scale calmly, just as light and motion unfold slowly across space. The emptiness of space dominates not only perception, but physical interaction. Collisions between stars are exceedingly rare, while gravity influences regions over millions of years. Even within dense clouds, the material is tenuous, expanding and contracting according to predictable laws. Space is both vast and orderly. As you rest with these ideas, Orion's structures begin to take a different form in your mind. Stars, nebulae, and clouds now exist in layers of size and distance relative to the solar system. Each layer is measured and comprehensible, grounded in observation and geometry. The familiar pattern is no longer abstract. It is embedded within a framework of scale. This calm understanding prepares the mind to expand further. If Orion can be compared to the solar system, then it is naturally part of a larger environment, the galaxy itself. Distances, motion, and structure on this scale follow similar principles, extended across a vast spiral of stars, gas, and dust. Thinking in ratios and orders of magnitude allows the mind to move outward without strain, ready to place Orion within its galactic context. You shift your thoughts outward once again, beyond Orion's molecular clouds and nebulae, toward the spiral structure of the Milky Way. The galaxy is a vast system, measured through the positions, motions, and brightness of countless stars. It is not an abstract swirl, but a physical structure mapped by decades of careful observation. The Milky Way consists of a flat disk of stars, gas, and dust, punctuated by spiral arms that trace higher densities of material. Orion is located in one of these spiral arms, known as the Orion Cygnus arm, or the local arm. This arm is a minor but clearly defined structure, positioned between two larger arms, Perseus and Sagittarius. Distances to various segments of the arm are determined using stellar parallax, spectroscopic parallax, and radio measurements of gas clouds. Measured from the center of the galaxy, Orion lies approximately 27,000 light-years from the Milky Way's core. Its position within the local arm places it in a region of moderate stellar density. Stars, gas clouds, and star-forming regions are distributed along this arm, with spacing and mass determined by observations across multiple wavelengths, from radio to optical to infrared. Orion's molecular cloud complex and associated nebulae occupy only a small fraction of this arm. The rest of the spiral segment extends for thousands of light-years, with star-forming regions spaced intermittently along its length. These measurements rely on distance determination techniques calibrated by parallax, allowing astronomers to place clouds and stars within a three-dimensional galactic framework. The spiral arms themselves are not static. They are density waves that move through the galaxy, compressing gas and triggering star formation as they pass. Stars orbit the galactic center independently of the arms, carrying them along while the waves propagate more slowly. Orion's material is embedded within this dynamic environment, participating in both local and global motion. Stars within Orion, as measured by proper motion and radial velocity, move at tens of kilometers per second relative to the Sun. These velocities are small compared to the orbital speed around the galactic center, which averages roughly 220 kilometers per second at this radius. Observing and measuring these motions allows astronomers to model orbits and predict future positions over millions of years. The solar system orbits the Milky Way's center along a nearly circular path. Similarly, Orion stars and clouds follow orbits shaped by the galactic gravitational potential. Small deviations from perfect circular motion, caused by interactions with other stars and clouds, are measurable and included in precise models of the galaxy's dynamics. These measurements confirm that Orion is bound within the galaxy, moving predictably through space. The local arm is rich in molecular clouds, H2 regions, and young stars. Orion's nebula and associated complexes exemplify this population. They are relatively nearby compared to more distant spiral arms, allowing detailed study of both structure and dynamics. Gaia and radio observations provide precise positions, revealing not only depth but also motion within the local segment. Even on this galactic scale, empty space dominates. Stars are widely separated, with typical distances of tens to hundreds of light-years between them. Gas clouds, while massive, occupy mostly empty volume. This perspective reinforces the same principle noted when comparing Orion to the solar system. The majority of space is unoccupied, and structure emerges from concentrations within a largely empty medium. Orion's placement in the Milky Way also informs understanding of its origin. Spiral density waves compress gas, creating regions dense enough for star formation. Orion's molecular cloud complex represents one such concentration. Its stars form over millions of years within this gravitationally guided environment, consistent with models of galactic structure and evolution. Observations across multiple wavelengths confirm the association between Orion and the local arm. Radio measurements of hydrogen reveal the cloud's position and velocity, while optical and infrared imaging locate the stars formed within it. Together, these data anchor Orion firmly within its galactic context. This perspective also highlights motion over time. While Orion appears fixed in the sky, its stars are moving along their galactic orbits. Over millions of years, the pattern will change. Some stars will drift out of the region entirely, while new stars form within the molecular clouds. The constellation as we see it today is a temporary alignment along our line of sight, yet its components remain physically connected within the larger arm. Placing Orion within the Milky Way does not diminish its scale. Its molecular clouds and nebulae remain vast, and its stars continue to dwarf planetary systems. What changes is context. These structures exist within a moving galaxy, embedded in an orbit around a dense central region that dominates gravitationally. Their properties are measured, predictable, and coherent within this framework. The calm certainty of galactic scale allows the mind to rest while expanding outward. You do not need to visualize the entire galaxy to appreciate Orion's place within it. Distances, motion, and relationships are all measurable. The local arm serves as a scaffold, providing a stable environment for both observation and comprehension. As you consider Orion's physical footprint, you notice that it is part of a layered hierarchy of scale. Individual stars and their associated gas clouds are nested within the local spiral arm. The arm itself is embedded in the galactic disk, which rotates around the center of the Milky Way. Each layer is defined by measurement, motion, and mass, forming a coherent system. This understanding gently returns focus to Orion itself. Its clouds, stars, and nebulae exist within the galaxy, yet maintain their own scale and structure. Measurement has provided clarity without diminishing wonder, revealing a network of relationships between star, cloud, and galactic structure. Orion is simultaneously a local system and part of a vast, rotating spiral. The hierarchy of scale emphasizes the reliability of observation. Distances, velocities, and masses are determined through multiple independent methods. These measurements converge to produce a consistent picture of Orion within the Milky Way. Observational precision replaces uncertainty with calm knowledge, allowing the mind to rest even while considering immense distances. Through this lens, Orion is no longer a flat pattern or a vague cluster. It is a physically defined region embedded in a galactic structure, moving through space along predictable paths. Its position, motion, and connections to the surrounding material are known. This clarity provides a foundation for understanding scale, size, and motion at cosmic levels. Orion remains recognizable in the sky, yet the measured reality beneath the visual outline adds depth. The molecular clouds, nebulae, and stars are all part of a three-dimensional environment within the local arm. This environment moves steadily around the galaxy, carrying Orion's material through space while allowing observation to trace its structure and motion. Resting with this knowledge, your mind appreciates Orion as a connected region within a rotating system, both vast and well-defined. The combination of distance, motion, and structure provides a calm framework in which the constellation exists, measured precisely and situated meaningfully within the Milky Way. You allow your thoughts to settle quietly on the idea of size. In everyday life, size is intuitive. A chair is larger than a cup, a house larger than a chair. In astronomy, these instincts are rarely reliable. Stars, clouds, and nebulae exist across distances, volumes, and masses that defy everyday experience. Understanding big in space requires careful definition and measurement, rather than visual impression. Astronomers consider several dimensions when describing size. One is spatial extent, the three-dimensional volume occupied by a star, cloud, or cluster. Another is mass, the total amount of matter contained within an object, whether concentrated or diffuse. Luminosity, while not strictly size, often relates to physical scale because larger or hotter stars emit more energy. Each of these quantities provides a different perspective on bigness. Distance plays a central role. Two objects may appear equally bright or similar in angular size, yet differ vastly in true scale. Measuring distance allows astronomers to convert angular measurements on the sky into physical sizes. Without this step, apparent size is misleading. A nebula 10 light-years across can look tiny if far away, while a closer cloud of similar dimensions may dominate the view. Volume is often calculated from measured size in multiple directions. A star's radius gives a spherical volume. A molecular cloud may be modeled as a series of clumps or filaments. The Orion Nebula, for example, has a measured diameter of roughly 20 light-years. Its volume is vast compared to the solar system, yet it is tiny compared to the full molecular cloud complex that stretches hundreds of light-years. Mass adds another layer of understanding. A red supergiant like Betelgeuse has hundreds of times the sun's radius, yet its average density is low, spread over a large volume. In contrast, white dwarfs contain similar mass to the sun in a tiny fraction of that space, producing extremely high density. Big depends on what property you are considering: volume, mass, or energy output. Luminosity is another measure that conveys scale. Hot, massive stars emit energy at rates far exceeding the sun. Rigel, a blue supergiant, shines tens of thousands of times brighter. Its physical size, surface temperature, and mass all contribute to this luminosity. By measuring light across different wavelengths and knowing distance, astronomers calculate energy output precisely, connecting it to fundamental physics. Apparent brightness, color, and angular size must always be interpreted in context. A nearby dim star may appear bright, while a distant supergiant may seem faint. Angular separation between stars can suggest clustering, even when depth separates them by hundreds of light-years. Measurement transforms perception into understanding, replacing instinct with evidence. Empty space dominates nearly every scale. Within the solar system, Planets are tiny points separated by vast distances. Within Orion, stars occupy only small portions of the molecular cloud complex. Across the Milky Way, even entire clusters and nebulae are scattered among almost empty interstellar space. Recognizing this emptiness is critical to understanding the true meaning of size. Logarithmic thinking is often necessary. Distances, masses, and luminosities vary by many orders of magnitude. A single planet, a star, a nebula, and a molecular cloud differ in scale so dramatically that linear intuition fails. By considering ratios or logarithmic steps, you can hold these vastly different sizes in your mind without distortion or confusion. Scientific terminology supports this precision. Terms like radius, parsec, solar mass, and light year provide measurable reference points. Radius describes physical size. Parsec defines distance. Solar mass standardizes mass relative to the sun. Light year expresses distance in a way aligned with the speed of light. Together, these units allow consistent comparison of objects across space. Volume, mass, and energy are interconnected. A massive star often has high luminosity but lower density compared to a compact star. A diffuse cloud may have enormous volume but moderate mass. Understanding big requires careful specification. Which property is measured, and how does it relate to others? Observations provide the data, while analysis interprets it in a clear framework. Measurement uncertainty is part of precision. Every value has a range of confidence, reflecting observational limits. Astronomers report these uncertainties transparently, allowing comparison and validation. Even when measurements are extreme, such as the radius of Betelgeuse or the mass of the Orion molecular cloud, uncertainty is quantified rather than ignored. This practice ensures that scale is scientifically robust. Scale is contextual. A star may dominate its local environment, yet appear tiny within a cloud. A nebula may stretch tens of light years, yet seem insignificant against the full molecular complex. The Milky Way itself is immense, and Orion occupies only a small segment. Thinking contextually allows the mind to grasp bigness without distortion or overwhelm. Dynamic processes also influence perceived size. Stellar winds, radiation pressure, and gravity all shape volumes over time. A nebula may expand or contract slightly, while a star evolves through phases with changing radius and luminosity. Observing these changes adds temporal scale, connecting physical size with duration and motion, further refining understanding. Measurements across different wavelengths provide complementary insight. Optical, infrared, and radio data reveal stars, dust, and gas, each with its own volume, mass, and energy properties. Combining these observations creates a coherent picture of scale, grounded in evidence rather than impression. Orion, its stars, and clouds are measured holistically, layer by layer. Your mind can rest with this layered understanding. Big is not a single quantity. It is a set of measurable attributes that interact in predictable ways. Volume, mass, luminosity, distance, and motion all contribute. The human intuition for size may fail, but careful observation and analysis create a calm, precise framework in which size becomes comprehensible. Even at the largest scales, from clouds to clusters to the Milky Way, the principle remains. Scale is contextual, measurable, and governed by consistent physical laws. Astronomers define size in ways that are testable and repeatable, allowing comparison across objects and distances spanning light years. What appears enormous visually can be quantified in detail, and what appears small may be revealed as vast when distance is included. This calm approach transforms perception. Orion is no longer only a pattern in the sky, nor only a collection of bright stars. It is a physical structure with volume, mass, and energy, embedded within a larger molecular cloud and spiral arm, moving predictably within the Milky Way. Understanding big in astrophysics means recognizing the interplay of these properties while maintaining clarity and precision. As you consider these ideas, the mind naturally prepares to synthesize them. Distances, depth, size, mass, and luminosity are all known. Stars, clouds, and nebulae exist in measured positions and volumes. Your perception can now rest, confident that Orion's scale is defined scientifically, with clarity replacing ambiguity, and wonder preserved alongside understanding. This reflection gently opens your awareness to the constellation as a whole, integrating distances, sizes, and structure into a calm, coherent view. Each measurement supports another, from parallax to Gaia data to mass estimates, forming a consistent picture. Orion is simultaneously familiar in the sky and comprehensively defined in space, ready for the final understanding of its true scale. You allow yourself to rest fully on the idea of Orion as a three-dimensional structure. The stars you have admired for years are no longer just points on a dark canvas. Each has a measured distance, a defined size, a calculated mass, and a well-established energy output. The constellation you once saw as flat now unfolds in depth, creating a tangible arrangement in space. Betelgeuse and Rigel dominate your attention, yet their prominence in the sky no longer equates to dominance in volume. Betelgeuse's red glow reflects a supergiant star hundreds of times the sun's radius, occupying a tiny fraction of the space separating it from neighboring stars. Rigel's blue-white brilliance is equally commanding, but it exists hundreds of light-years away from other bright stars in Orion. Their sizes are immense, yet the distances between them dwarf their volumes. The belt stars, Alnitak, Alnilam, and Mintaka, form a line familiar to the eye, yet parallax and Gaia data reveal that these stars are separated by tens to hundreds of light-years. Their apparent alignment is a visual coincidence, a projection of three-dimensional space onto your night sky. The pattern remains comforting and recognizable, but you now understand it as a map layered with depth. Extending beyond the stars, the Orion molecular cloud complex occupies hundreds of light-years. Within this cloud, the Orion Nebula shines as a luminous pocket of ionized gas, roughly 20 light-years across, housing active star formation. Dense cores within the cloud condense slowly into new stars, while the surrounding material remains tenuous and spread out. The nebula and cloud together demonstrate that structure is present on multiple scales, from individual stars to clusters to extended regions. Mass measurements clarify another layer of scale. Individual stars like Betelgeuse and Rigel contain many solar masses, while the molecular cloud contains hundreds of thousands. Even though volume dominates, mass is concentrated in discrete regions, giving rise to gravity-driven processes like star formation and cluster evolution. The balance between volume, mass, and density provides context for every physical process you have considered. Distance remains central to understanding scale. Angular separation in the sky, while familiar visually, translates to immense physical separations when combined with measured distances. The nearest stars in Orion's belt are over 700 light-years away from Earth, while clouds behind them extend hundreds more. Knowledge of depth turns a flat constellation into a measurable three-dimensional system. Luminosity links scale to energy. The stars emit radiation across the electromagnetic spectrum, with surface temperatures determining color and total energy output. Betelgeuse and Rigel alone emit thousands to tens of thousands of times the sun's energy. Combined with distance, this emission explains apparent brightness and provides insight into stellar life stages. Energy scales coexist with volume and mass to create a complete physical profile. The molecular clouds introduce additional complexity. Infrared and radio observations show gas and dust distributed over large regions, with density variations forming filaments, knots, and cavities. Star formation occurs in localized cores, often obscured from visible light. The integration of multiple wavelengths allows a comprehensive understanding of both structure and activity. Observing Orion within the Milky Way adds a final layer. The constellation resides in the local spiral arm, approximately 27,000 light-years from the galactic center. The local arm is a density wave in which gas and stars are concentrated, guiding star formation over millions of years. Orion's motion follows galactic dynamics, orbiting the center at roughly 220 kilometers per second. Its components are not static. They drift, evolve, and interact according to gravitational laws. Empty space dominates every scale you consider. Even within dense molecular clouds, matter is sparse compared to laboratory vacuums. Between stars, volumes expand across tens to hundreds of light-years. Emptiness defines the context in which structure arises, reminding you that cosmic scale is measured as much by the space around objects as by the objects themselves. Logarithmic reasoning helps unify these scales. Distances, sizes, and energies vary by orders of magnitude, yet can be compared using ratios. The solar system is a tiny feature within a star-forming region, which is itself a small segment of the galaxy. This perspective allows the mind to integrate scales without distortion or confusion, placing Orion within a hierarchy of cosmic structures. Understanding big in Orion now includes multiple properties simultaneously. Size, mass, and luminosity combine with distance, density, and motion to create a measurable, coherent system. Visual appearance no longer dominates your perception. Evidence-based measurement defines reality. This precision does not diminish the wonder you feel, but anchors it in fact. The constellation's familiar outline serves as a guide for exploration, not a literal boundary. Star clusters, molecular clouds, and nebulae occupy overlapping regions, forming nested structures. Angular patterns provide orientation, while measured quantities provide physical meaning. Depth, size, and energy together define Orion, producing a calm, complete picture. Timescales complement spatial understanding. Stars in Orion evolve over millions of years, clouds condense over similar periods, and galactic motion occurs over hundreds of millions of years. Observation captures snapshots within this vast timeline, allowing inference of processes and life cycles. Change is measurable, predictable, and gradual, reinforcing the calm of understanding. Measurement uncertainty remains a companion in this process. Each distance, mass, and radius has a quantified confidence interval, reflecting observational limits. These uncertainties do not obscure knowledge but provide transparency. They ensure that the scale you hold in mind is grounded in reality, while remaining precise and reliable. By integrating all layers, stellar sizes, distances, clouds, nebulae, and galactic context, Orion emerges as a defined, measurable structure. It is no longer only a pattern of bright points. It is a region of space with volume, mass, energy, motion, and timescales, all quantifiable. Observation transforms perception into calm, rational comprehension. You may notice that this understanding preserves visual familiarity. The constellation's outline remains recognizable. Your eyes see the same stars, but your mind now holds a richer, deeper knowledge of what those points represent. Pattern and measurement coexist, reinforcing both recognition and scientific insight. The synthesis of data from parallax, Gaia, radio and infrared mapping, spectroscopy, and motion studies forms a coherent framework. Every measured property contributes to the full picture. Distances clarify depth, luminosities define energy, volumes reveal scale, and motion situates Orion within the Milky Way. Knowledge replaces uncertainty, yet the sense of awe remains intact. Orion's true scale can now be appreciated as simultaneously familiar and immense. Stars shine brightly in the night sky, nebulae glow in measured detail, clouds stretch across hundreds of light-years, and the constellation moves steadily through the galaxy. This layered understanding allows the mind to rest in both precision and wonder. As your awareness settles, you perceive Orion not as a flat pattern, but as a living, measured system. Depth, distance, size, mass, energy, and motion are all integrated into a calm, coherent picture. Knowledge reduces mystery, yet the quiet beauty of the constellation remains. Observation has transformed Orion into a known structure, one whose scale is defined, comprehensible, and gently inspiring. You rest with the realization that the stars above are not merely points of light, but components of a system governed by consistent physical laws. Orion is a constellation you can now place confidently within space, measure quantitatively, and appreciate for both its size and its order. Its structure, once imagined, is now gently understood, leaving the mind at ease while curiosity quietly lingers.